My name is Lauren Milliken. I'm from MIT. I work in, research computing. Some of my co-authors, Vijay and Jeremy, are from MIT Lincoln Laboratory. And Hayden Janathan is a PhD student at Vanderbilt, but also comes and collaborates with us fairly frequently. So he's working with us over the summer on the Python D4M implementation. So what I'm going to do is introduce to you sort of some of the newer implementations of D4M, which I'll explain later. Previously, it was available in MATLAB, which is great for the sort of the scientist and engineering fields, but branching out into these newer languages opens it up to a broader community. Okay. And one of the nice things about D4M is it does have the ability to connect to and interact with Accumulo. So that's why we're here. Okay. So first I'm going to introduce D4M and what has been done in the past, what it's used for. I'll talk a little bit about the Julia and Python D4M database connectors. I'm not going to talk so much on the other aspects of the library. I'm going to go through and do a demo for you guys, and then we'll conclude. Okay. So D4M stands for Dynamic Distributed Dimensional Data Model. It's a library that allows you to represent various types of data as the structure called an associative array, which I'll explain in a moment. This will allow you to use linear algebraic operations to manipulate your data, and it can allow you to connect to and query high-performance databases, including Accumulo. An associative array is two keys mapped to one value, so sets of keys mapped to a value. You can think of them, the way I like to think about them, are big sparse matrices, where you can index into that matrix not only with numeric indices or integer indices, you can use strings as well. And this is what allows you to sort of map text data into something that looks more like a matrix and allows you to do linear algebra on it. You can also easily represent graphs in this sort of structure, so you can think of mapping this to an adjacency or an incidence matrix. Another important thing is associative arrays are closed under algebraic and set operations. What that means is you do an operation on an associative array or two associative arrays, you get another associative array back. And what that allows you to do is chain together these operations to create more complex analytics. Finally, you can do the same thing with array indexing. When you index into an associative array, whether you're using numeric or string indices, the result is going to be another associative array so that you can continue to run your analytics on that as well. And that's sort of where things like dictionaries, for example, which is a similar data type, differ. A dictionary will give you the value as opposed to a subset of that dictionary. Okay. As I mentioned, D4M was implemented originally in MATLAB because most of our users are scientists and engineers. They're used to high-level programming languages. But what's happening more recently is more scientists and engineers are using things like Python and Julia to do their analytics in. So we're branching out to those languages as well. I'd also like to mention that it's very easy to remember our website. You just go to dform.mit.edu, and that'll point you to all of the download links for all the different versions. Okay. So I mentioned that D4M can represent, using associative arrays, a variety of different data types. You can do sort of the traditional set operations using kind of SQL-style data. You can represent these dense tables with an associative array. You can also represent sort of more the sparse graph-type data, a little bit more akin to the NoSQL or the Accumulo type databases. And you can also represent data that's sort of in this array type database structure. Obviously, today we're talking about the graph operations, the NoSQL databases. Okay. And I mentioned that associative arrays support linear algebraic operations. These are just some examples. We can do something like matrix addition, where the associative arrays don't actually have to be the same dimension, which in a matrix they do. In an associative array, if the the keys don't match, it just basically almost does a set union of the keys. And then the keys that do match, it'll add those values together. And then you can also do things like matrix multiplication, and you can sort of overload the plus and the times as well for the matrix multiplication to create more interesting analytics. Okay. Now I mentioned that we've implemented this in both Julia and Python. Sort of obvious why we chose Python. A lot of people use Python. A lot of you are probably very familiar with Python. But we also picked Julia to implement. And I wanted to take a moment to introduce Julia because I know not a lot of people are very familiar with it. Can I see who has used Julia or has heard of it? Okay, we've got a couple of people. Great, great. So Julia is a fairly new language. It's been developed for scientific and numeric computing. And it's a language that was, from the very start, developed with a focus on both being high level and high performance. So we want something that people can use easily, has the ease of use of, say, Python or MATLAB, but has the performance of something more like C. One of the ways they do this is they have a just-in-time compiler, which compiles the code down into LLVM code. And that runs pretty quickly. So you'll find the first time you run something in Julia, it might be a little bit slower, but then the next time you run it, it'll be super quick. It's used in a lot of different fields. I know particularly the mathematical optimization field has really adopted Julia, and they have their own optimization toolbox that they have that'll call a lot of the enterprise toolboxes as well. And it's been shown to scale well on HPC systems. Particularly, I really like their distributed arrays package, which allows you to do distributed computing by just changing a data type. Okay. So now I'm going to talk about Julia and Python's database connector. So a lot of the set operations and the algebraic operations in D4M are going to be similar to the way you would do it in the language. So doing plus in D4M Python will be a lot like doing plus in Python itself. So we tried to keep that. So that's all I'll say about the actual library implementation part before I move on to the database stuff. Okay, so this is where I usually like to walk over and point at things, but I'll use the mouse. So with Julia, basically what we have here is we have this Accumulo connector that's written in Java. It's the same one that's used for the MATLAB implementation. And what Julia does, Julia uses the Java call package, which will spin up the JVM with the Accumulo connector on its class path. So it's pretty straightforward and pretty simple to do. With Python, it's a little bit more complicated. We're using Py4j, which doesn't by default, at least as far as we've seen, start up its own JVM. So what we do is we have this start Java function that will use the subprocess module to start up the JVM with this, which sets up the Py4j gateway. Okay. Then, as I mentioned, once all that is set up, both the Python and Julia implementation as well as the MATLAB implementation use the same D4M Accumulo Java library to connect to Accumulo. Okay, so that makes things pretty simple and interoperable. You know that something that works in Julia will probably work the same way as it would in Python or as it would in MATLAB because it's calling the same underlying code. Okay. Just to get an idea of what this looks like, both have some sort of setup function where you say the name of the database instance and you optionally give it a configuration file. I will say if you're running it on our system that we have over at MIT, you actually don't need to give the configuration file. We have that all set up so it knows where to look up the password and everything. You can create tables. So it's almost like an indexing operation into the database, if you think of it that way. You can insert data, you can query the data, and then you can also delete tables. Okay. Let's see. So we have some time, so I'm going to go through this next bit. I'm going to kind of show in diagrams what's going on in this. I'm going to show it using the Julia version, but the Python would be very similar. Okay. You connect to the database. It'll start up the JVM with the D4M Accumulo connector in there, and it connects to Accumulo. So pretty simple. When you're creating a database, it'll call the create table function. And I will say that for the sake of the slides, these function calls are notional. Java calls tend to be very verbose and don't like to fit on slides. So that's kind of what goes on. One thing I want to point out, is we support table pairs. So often you'll have, say if you're representing a graph, you have an edge table, and then you want to also store the transpose, and that allows you to do quick column queries as well. So when you create a database table pair, the D4M package will automatically create two separate tables in your Accumulo. Okay. Similarly, when you insert data into a database table pair, it'll put it first into the main edge table, and it will also do the transpose for you as well. It'll transpose the data and put it into the transpose table. Okay. When you query on the row, it'll automatically query on the edge table, and when you query the column, it'll automatically query on the transpose table. So you don't have to do that, and it'll return it back as if you had queried on the original table. So you kind of get, as an analyst, it's really helpful to get sort of what you're expecting. You don't have to worry about moving things around or thinking too hard about which table you're going to query. And finally, and then this is the data you'd get back. Finally, if you wanted to delete your data or your tables, which production doesn't make sense, but when you're testing these things is very helpful, you can just call delete and it will delete. So these are some scaling plots for the Julia implementation, comparing ingest rate and query rate with the MATLAB implementation. The solid lines, because I know these are probably a little bit hard to read, the solid lines are the Julia implementation, and the dotted lines are the MATLAB. In this plot here, we're scaling with the number of ingesters, or the number of processes that are ingesting at the same time. And each of these different colors represents a different size graph. So you can see we have fairly good scaling. And for the most part, the Julia implementation is faster than the MATLAB implementation. This is a plot showing scaling in terms of the graph size. So as the graph gets larger, you see that eventually it sort of does start to peter off a little bit, but you still have fairly consistent scaling with graph size as well. I'll point out, you'll notice that there's sort of this peak over here in the 13 to 14 scale graph. And the reason that is we ingest our data in batches, and after that size, that's when the first batch fills up and it starts having to do it in more than one batch. So that's what that is. It's a common question. This is comparing the query rates. So on the x-axis here, we're looking at what sort of are the expected return sizes. So what's the approximate degree of the vertices we're querying? This is sort of in terms of graphs. And you'll see the dotted lines and the solid lines are fairly close together. So you get similar scaling across MATLAB and Julia. Okay. Now I'm going to attempt to do a live demo. So we'll see how this goes. It's always dangerous. Okay, is this the one I want? Yes. Okay. So I'm going to start with Python. I'll move to Julia, and if I have time, I'll show you guys a couple things in Graphulo using Octave. Okay. So with Python D4M, you can actually, as I mentioned, you can go to d4m.mit.edu, click the download link, and it'll point you to a GitHub repo where you can clone the repo and run this Python setup install. That'll install at the right place so that when you open Python, you can run import, and it'll import. Okay. So first we're going to create this sort of dummy associative array. Which is what it looks like. You have a list of row keys, list of column keys, and a list of values. And these are triples, so the number of rows, columns, and values are going to be the same. In a D4M kind of string, we like to, because it kind of started out in MATLAB, that's one of the reasons it's formatted like this, we put everything together in a single string, and the last character is the delimiter. So you can choose whatever delimiter you want. So depending on your data, you might choose something else. For the sake of a demo, a comma is a nice delimiter to use. But if you're using free-form text data that has commas in it, it's not a great one to use. So that's what that's about. So we can create an associative array this way. And then this is what it looks like with a string value. So this is sort of the full expanded view of it. And then this is what it looks like if you were to put numeric values in there. And then you can do that just by calling logical on it. And that'll just stick ones wherever there's an entry and zeros where there isn't. And that allows you to quickly get to a place where you can start doing math with strings, which is very interesting. Okay. So this is what an associative array kind of actually is on the inside. You have this array of row indices or row keys, an array of column keys. In this case, we're looking at a logical. So, and then we have the sparse matrix on the inside. And the sparse matrix, if the values are numeric, will contain the actual values. If the values are strings, these values will actually be the index into the value array. Okay, if that makes sense. It's getting a little technical, but we can do indexing. It's pretty quick. So you can say, get me these 3 columns and get me A through AAA, those rows. So these are these columns. Those are the rows. And then we can also do math on these things. So we can add A and then that thing I queried earlier. And you'll see now there's 2s wherever this was. We can subtract things, which is almost like a set operation. It'll remove rows if the value goes to 0. Remove rows and columns. So you get this if you subtract A through AAA. So now we just have the B's down here. You can do an element-wise multiply. Look something like this. And then we can also do a matrix multiply. In this case, you'd get something that looks like this. Okay. So this is kind of a quick, let's read in some data from a CSV file. Often data kind of looks like this, very spreadsheety when it comes in. In order to do graph operations or math, a lot of the times what we want to do is make this data sparse. So we can do that in a few lines of code here. And now we have sparse data. This is actually transposed just so it's easier to read, but these would be the row keys, which is these are the file names. This is data from news articles, by the way, with entities extracted, so location, person, time. So these would be the column keys, and these values are actually the position in the text that entity occurred. Okay. And then because we like plots, we can plot this in sort of a spy plot, and this shows us what kind of a notional idea of what our data looks like. Oh, this is actually we did a matrix multiply, and then we did a spy. So this is changing it almost into an adjacency matrix, which entities occur with each other, and then view that. So you'll see this is fairly dense area. Here's some dense areas. This is the diagonal, which a lot of times will just end up being a bunch of ones or be very dense unless you remove it. Yep. So that's sort of the in-memory, gives you a flavor of what the in-memory deform operations are and how you might use it for analyzing data. I'm going to go to Julia to show some of the database operations. Okay. So it's a similar story for Julia. To get it, you want to go to the download page on deform.mit.edu, and then you can clone the Git repo into Julia using this command. I will say we are working on moving to Julia 1.0, which has a different package manager, so the operation would be a little bit different. And we're also working towards registering it as an official package, so you can get it that way. So in Julia, you just say using. So I'm going to use D4M and this other package that just loads files, pretty much. Can set up a database. Now we're connected. And then you'll see here, this is the actual database, so I'm not pretending I'm connecting to a database. We can see what tables are in the database just by doing ls. We can create tables or connect to them by calling the DB. So this is actually sort of like an indexing operation. So it just created these tables, and now when we list it, we'll see these extra tables. And so you can see them here now. Okay. And then I made this table by accident maybe, so I want to delete it, and we can delete it, and it's gone. Should refresh a second. Yeah. Okay. So now let's look at loading some actual data. This data is from the OpenEdX course platform, which is an open source course platform you can put your own courses up on, and online courses, and it actually collects a lot of information about the students using the course through tracking logs. So it's sort of like clickstream data. And I did a demo a few months ago using this data and this D4M Julia package. So I have this already available and parsed out nicely. So this is kind of what the data looks like. This corresponds to one event in the tracking log. And then we have these bits of data. So these are sort of like the fields, and then these are sort of like the values of that field if you think of the dense form. And then this is the sparse form. So what we tend to do is we put the value up in the column qualifier with the sort of the label. Okay. So this is a problem event. So a student's submitting a problem and it's getting graded. It's happening in this module. This is the name of the section. So you can see that's sort of the data that it is. We have the username, the timestamp. To put this in the database, we just call put. And it's pretty quick. It's not a lot of data. Didn't want to make you sit here forever and watch me ingest data. So let's see. There we go. There it is. So it ingested too quickly for the monitor to catch up. But yeah, so it's in there now. You'll see I also ingested into this degree table as well, which tells us how many times each column appears, each column key appears. And that kind of helps us plan for queries, what we might query first, and things like that. It's just useful data to have. My notebook. Okay. Now, this is a nice Julia functionality that allows you to time things. It's called a macro. So I'm going to time this. So I'm run it twice. There we go. So this is a row query. This is a column query, and you'll see they're pretty similar timings. And I think this is sort of like in the range of random, which one's going to be faster than the other. And these are the size that we're getting back. So you'll see we're getting one row with a bunch of columns, and here we're getting one column with a bunch of rows. Okay. You can also query multiple keys at once. So if you want to specify two events, say, in our data, or you want to specify a range, you can specify a range. You can also use this handy starts with, which will get you all of the keys that start with that prefix. Okay. Great. So I believe, let's see. I think I have 15 minutes. So I think I have time. I'll show you guys. Does anybody have any questions on this part so far? Okay. So I'm going to show you guys some Graphulo stuff. Graphulo is basically a set of server-side iterators that sit in Accumulo that allow you to do graph analytics inside Accumulo. So we've implemented a set of almost basic graph kernels, so things like matrix multiply that allow you to build those up and build out more complex analytics like breadth-first search, Jaccard coefficient, things like that. So this is implemented in Octave. This is a lesson I did on a graph course a few months ago, actually. So let's see. So we're connecting to the same database. And you'll see the syntax is a little bit different between the languages because we didn't want to use the same syntax for every language because the idea is to bring the library to the people who are using that language, not force them into some preconceived idea of what the syntax should be based on the first language we implemented in. Doesn't really make sense. So we create these tables. We're going to ingest some Twitter data. Don't need that. Last time I did this, it was pretty quick. Refreshing. Yeah, there it goes. There it is. And now, so what we ingested is this similar schema. We have an edge table, a transpose table, and a degree table. This is data from Twitter. So our columns are, so each row is a tweet, and our columns are things like username, the parsed out words in the tweet, the timestamp, things like that. So the first thing we might want to do when we're running a graph analytic is we have all this data. It's in sort of this incidence format, but maybe we want to look at some adjacency matrices. So here are sort of some like columns that we might want to do these on. So maybe we want to look at real words, so words that start with actual letters. Maybe we want to look at hashtags. We might want to look at tweets at someone. Username, we might want to look geographically. Okay, and this is querying the degree table, and we can see these are sort of the number of entries that have these sorts of things available. Okay. So here what we're going to do is we're going to multiply two tables in order to create an adjacency matrix. So we're going to create a word-word matrix by multiplying the columns that correspond with actual words, transpose with the other one, the same thing, pretty much, so that you can get words versus words. Okay. There we go. And it's pretty quick. Let's see. We have it here. Here it is. So there's the word graph. About 500,000 entries. Can make some other graphs. This is saying it's important to decide what order you do the multiplication in. What's table A and what's table B. It makes a difference. So if you pick the wrong one, it's very slow. If you pick the right one, it's very fast. Let's see. Get something more interesting. So we can, using this, we can do a breadth-first search, degree-filtered breadth-first search. So first we're going to create a degree table from our new graph table, and oh, that was one I didn't create. This is the one we want. Okay, that was quick. It still doesn't like it. Oh. Which one do we want? Just the users. Anyway, if I had looked at this ahead of time. Oh, I have to run all of these. That's why it's complaining. That's right. Okay. I thought I could pick and choose. So here we're creating a hashtag graph. Here we're creating a user hashtag graph, so which users are using which hashtags. And then here we're creating sort of a user graph, but using that hashtag user graph. So we get graphs showing users that use the same hashtag. So it's kind of this built-on thing. Okay. And then this is the graph that we're running Depthfirst search on. So first we generate the degree table so we can do degree filtering. And we're say maybe these are users we're interested in. And we're only interested in the users that have degrees maybe greater than 5 but less than 20. So remove people who only tweeted once and get rid of people who tweet every 5 seconds. And we can run our Depthfirst search. And then we did 2 hops. So starting from these 3 users, everyone 2 hops away. They use the same hashtags, so we get this nice community of people that all kind of talk about the same thing, maybe. Okay. Let's see. I think at this point, I'm going to get to my conclusion so we can answer some questions, and then if we have time after questions, I can show you some more if you'd like. Okay. Okay, so to conclude, D4M is a library that will allow you to do analytics on heterogeneous data. So very diverse types of data. You can do linear algebra operations, you can do set operations, you can index into it. Everything you get out will be another associative array, so you can continue your analytics and chain together more complicated things. Okay, both D4M.jl and PID4M, sort of what we're calling them, they implement this associative array data structure and also allow you to perform database operations in Accumulo using D4M's custom database connector. I've shown a couple performance tests for the Julia connector. I think one of our next steps is to do those same performance tests for Python, see how they compare. I personally like Julia, so I'm kind of rooting for Julia. I think that Julia's performance is really great. And the things that we're looking at doing next in the short term, as I mentioned, we're upgrading the Julia implementation to Julia 1.0, which was just released this August. That's sort of the step into being a mature language for Julia. So this will be where a lot of their breaking changes will stop. So it should be fairly consistent and easy to upgrade from there. Also a nice new package manager, other things that we're very excited about. We're working on right now implementing the Graphulo calls from the Julia D4M and the Python D4M. I've definitely made some progress on the Julia side, but it wasn't quite ready for today. And then also important to some people is implementing these interfaces for other databases as well. So you can maybe get data from multiple sources and combine it together. It would be really cool. And I have the URL down here, so you don't have to memorize it if you wanted to write it down. And I'll open the floor for questions. Yes. Implementation of what? Sorry? Depthfirst search? Yeah, it's Depthfirst search. That's a little bit harder to do. I don't think you can do that with it's harder to do because it's a very iterative method. So, and it doesn't have as good performance as Depthfirst search for finding things, just because the number of iterations can get very long for Depthfirst search. But you could definitely sort of do it on your own with matrix multiplies and chain those together. Okay. We have any other questions? Yes. Support what? I'm sorry, I can't hear you. Tensors of greater than 2. So I think that there isn't, but one way you can, sort of the way we do that is we just kind of roll it all out into one big wide thing, which is sort of how Accumulo works, right? You don't have a third dimension, really. You can kind of think of the column family maybe that way, but it's still kind of, yeah, exactly. So I think even if you did do that, you might still need to roll it out to do operations sometimes, so. Okay. Yeah, of course. So it does. I'm not sure if I understand. Oh, okay. Yeah, so these are built on sparse matrix libraries that already exist. So if they support that, if they take advantage of that, then it does. But we're not really in the business of rewriting sparse matrix libraries. Does anybody have any other questions? Maybe about, I don't know, the Python implementation. I know people have been asking for that for a while. No? Okay. Does anybody want to see more of the Graphulo demo, or we done? Yes, you do? Okay. Yeah. So, okay, we'll get back to that then. And feel free to stop me and ask questions too. I'm more used to that format. Okay, so everyone can see this, right? I should have asked at the beginning. It's kind of hard for me to see it from here. Okay, so Jacquard index gives you an idea about how similar different vertices are. So maybe we're interested in that user graph again, and we want to see what users are similar, kind of on a grand scale. So here we're not doing any column filtering. We're just looking at who are the similar users, and maybe who are the users that are the most similar. So we're kind of looking at that. You can see this is a fairly small data set, so it runs very fast. But it's actually, you would think that running in the database, it's going to be slower than running in memory. But for things like Depthfirst search and Jacquard, when you get to the larger graph sizes, it actually tends to be very similar. And at some point on your computer, you're going to run out of memory, and that's not a problem in Accumulo. So that's very nice. These are kind of the similar users. Let's see. And then the final example I have here is a topic modeling example using NMF. So we're looking at this, in this example, what we're doing is we're looking at the users found in Depthfirst search example. We found this community of people that all talk about the same thing. What is it that they talk about? So we're running this to see what that is. So this is the Graphulo call here. And here we're getting, yes. Yeah, so first we're doing a Depthfirst search. And then we're just going to filter out the words from the Depthfirst search, from those users. And then we can run NMF on that graph of the words here. Okay. And NMF is one of those algorithms that would be faster running locally than running it in the database. But if you get to the point where your data just doesn't fit into memory anymore, the database is sort of all you have left. So at least you can even do it, even though it takes a long time. The algorithms like that tend to be the very long iterative ones where there's no predetermined like conversion, right? So it just kind of goes until it hits some optimization point. So it takes a little bit longer. But I think I had told it only a certain number of iterations. maximum of 10 iterations. So these are all come pre-implemented in Graphulo, the ones that I'm showing today. There's also, I believe, some implementation for triangle counting as well, if you're interested in that. So we're at iteration 9, so it's almost done. Oh, maybe, are we done? Oh, we're done. Great. So here are these topics. Unsurprisingly, it's a language we don't understand. Well, maybe somebody does in the audience. I don't remember what language it is from when I did this. So these are the 3 topics we found. Here are some of the top words in each topic. And at the time, I actually went back and put these into Google Translate to get an idea of what these words were, because I couldn't evaluate whether these were good or not. But you'll see topic 1, it's sort of, it makes sense. They're talking about leadership, discipline, doing good work kind of thing. This one was actually a bunch of the same tweets being retweeted. So it was something about a presidential nomination going on. And this one was a little bit less easy to understand. But this topic, I liked this one. It kind of made sense. So it's always a guessing game whether you're going to find something that makes sense with these things. It's really a lot of parameter tuning. But anyway, that's it.